All right. This lecture's going to be split up into 3 videos now. Hate that. Function composition. Okay. Function composition. A lot of notation, so it might seem hard at first, but it's actually a pretty simple idea. We'll try and draw some pictures to make it really simple, but let's try out its exact definition first. We're starting the next section. Composition. And our first definition. Let A, B, and C be sets. Let A, B, C be sets. And let F be a function from A to B. And G be a function from B to C. Then G composed with F is a function from A to C defined by G composed with F of A is equal to G of F of A for all A in big A.
Oh, we know this one. Yeah, not in this class, but.
Yeah, functions definitely came up in logic, came up again in topology, now it's coming up again here for those of you who have done all those things. Can't get away from functions. Okay, so let's try and just get comfortable with what exactly function composition gives us. So we need 3 sets really quick, A, B, and C. Doesn't really matter what they are, we're just going to make a picture of it. A, give me some numbers.
1, 2, 3, 4.
Give me some more numbers.
5, 6, 7, 8.
Give me some more numbers.
8, 9, 10.
11, 13, 15, 19. Okay, so we've got these 3 sets. And we're going to represent pictorially. And what do we want F to do? So F needs to be a function from A to B. We can make it however we want. What do we want F to map 1 to? 6, 2,
5,
3,
6,
4.
7.
Now we're going to make G. G is a function from B to C. You can make it however you want. All we know is it's a function from B to C. 5 goes to
13,
6 goes to
14,
7 goes to.
11.
Okay, so we've got 2 functions. F is a function from A to B. G is a function from B to C. And you understand what I mean with this picture, right? Tell me one ordered pair in F.
1, 6.
1 6 is in there, right? 4 7's in there. Tell me an ordered pair in G.
7, 11.
7 11 is in G. Okay, so you see how pictorially we're representing 2 functions.
Yes.
So G composed with F, we know that G composed with F is a function, we don't need that. G composed with F is a function from A to C by G composed with F of A is equal to G of F of A. Right? So G composed with F has to map everything in A to something in C. So what is G composed with F of 1 equal to? Well, that's equal to G of F of 1, which is equal to, what's F of 1?
6.
What does F map 1 to?
6.
6. So G of F of 1, which is 6. What's G of 6?
15.
15. So G composed with F of 1 is 15. Notice we're just doing both the functions in one go. We took 1 and mapped it to 6, and then we continued to 15. So it's like a way of wrapping these functions together into one function. You see that? Let's do another one. What's G composed with f of 4? So she already looked through, she said, well, 4 goes to 7, 7 goes to 11, therefore it's 11. Yep, and we can also say it the long way. G composed with f of 4 is G of f of 4, which is equal to G of 7, which is equal to 11. It works. What are the odds? Okay, so there's some examples. Let f from that to that. What is G composed with f? Okay, so let's do function composition with some more involved functions. So, example, we have f is a function from z to z by f of x is equal to x squared plus 1, and g is also a function from z to z by g of x is equal to 2x minus 3. Okay, so first off, what is G composed with f? Of x equal to? It's equal to G of f of x, right? What's f of x? So it's G of x squared plus 1, which is equal to 2 times x squared plus 1 minus 3, which is equal to, huh? You're confused going from here to here? Okay. If I say that f of x is equal to x over 2 star minus square plus x, and I ask you for what is f of, give me any shape, triangle. What's f of triangle? It's equal to triangle over 2 star minus square plus triangle. Whatever is in here, go through and replace all your x's with it. That's what we're saying. Whatever is in here, go through and replace all your x's with it. So we're going through here, and we're replacing all our x's with this.
Oh.
Okay.
No.
So, and then that's equal to, let's see, 2x squared plus 2 minus 3 is 2x squared minus 1. Right? So now let's try something and let's see if this really worked. So let's look for G composed with f of, give me a number. 3. So that should equal G of f of 3. What's f of 3?
3 squared.
Which is? There you go. 10. And what's G of 10? 17. Okay. So we said G of f of 3 is 17, which means when we plug in 3 here, we better get 17. What's 3 squared?
9.
Times 2?
18.
Plus 1?
Minus 1.
17. Okay. So it looks like it's working. Now let's do it the other way. What is f composed with G of x? Let's go back and look at this one real quick and look at that. So over here we wrote G composed with f of x. When we're looking at this picture, what is f composed with G of x? What's f composed with G of 1, for example? that's the same thing as f of g of 1, which is equal to,
There's no one.
it doesn't work.
Yeah.
It's breaking.
Yeah.
What about f of g? Let's see what's something g knew how to map 5. So f of g of 5 is equal to f of g of 5. What's g of 5?
Wait, we don't. It's 13.
13. So what's f of 13?
You can't. This is so.
Why isn't it working?
You have to start with C.
Right. The output, the image of f, has to be a subset of the domain of g. G has to be able to map the outputs of f to something. So, when we did g composed with f from a to c, notice in order to compose, you have to have f goes from a to b, and g goes from b to c. G has to pick up where f leaves off. Otherwise, you can't compose them. So that's why we can't switch directions here. Over here, we can switch directions, though, because f takes from the integers to the integers, and then g takes from the integers to the integers. So you can do f composed with g or g composed with f, doesn't matter. They'll just give you different functions. So now let's look at g composed with f composed with g of x real quick. What is this? This is f of g of x. What's g of x? 2x minus 3, right? And now we have f of 2x minus 3. What is that?
4x squared plus 4x plus 10.
Too fast. We got to start with 2x minus 3 squared plus 1, right? Plug that in for, where are we? For your x. We have x, whatever was here, squared plus 1. Whatever you plug in, squared plus 1. Whatever you plug in, squared plus 1. You with me so far? Okay. What is this squared? 4x squared minus, give you a hint, all 12x plus 9 plus 1 is equal to 4x squared minus 12x plus 10. Notice that and that are very different functions. So just because you can do both g composed with f and f composed with g does not mean they give you the same function. So first off, you might not even be able to do both of them, as we saw over here. And even if you can do both of them, they're still very different functions. The same way that 1 divided by 2 and 2 divided by 1 are very different numbers. Right? Okay. Yeah, we already made that point. We already plugged in. Next proposition. Good with this example?
Yeah.
Okay. Prove let A, B, C, and D be sets. Basically, we're going to prove that function composition is associative. So let A, B, C, D be sets, and let f be a function from A to B, G be a function from B to C, and H be a function from C to D. Then F, which one do we want to do first? Oops, we gotta do that last one. H composed with G composed with F is equal to H composed with G composed with F. So we're proving that function composition is associative. you've already come across associative operators before, right? Like plus is associative. Multiplication is associative. Do you understand what I mean by associative?
Yes, yeah.
If we do compose those together and then compose it with this, it's the exact same thing as if we compose those together and then compose it with this, as long as we don't change the order here. With me?
Yes.
Okay, so we're trying to prove that two functions are equal. In general, how do we prove that two functions are equal? Two functions are equal if they have the same domain and they map everything in their domain the same way. Does that make sense? Two functions are the same if they have the same domain and they map their domain the exact same way. Then the functions are equal. So when you're doing proofs where you need to show that two functions are equal, notice those are two functions, we're trying to prove that they're equal, we need to show those two properties. They have the same domain and they map the same way. So 1, observe that the domain of H composed with G composed with F is equal to. When you do function composition, what is the domain of your function? Where do you start? So when we did G composed with F, the domain of the composition is just the domain of the right-hand function. Right?
Yeah.
So when we're looking at F composed with G, the whole function taken together, it still just maps everything in its domain is A. So it got its domain from A, but it's got its image from C. Does that make sense?
Yes.
So the domain of H composed with G composed with F is the exact same thing as just the domain of G composed with F, right? Whatever the domain of this function is, it has the same domain as this function. Because when you're composing two functions together, the domain of the composition is the same thing as the domain of the right-hand function.
And then it's just the domain of
Which is equal to what?
domain of
Domain of F, which is equal to what? A. Now, let's look at the domain of the other function. Of H composed with G composed with F is equal to, we have a composition of two functions. The domain of the composition is just the domain of the right-hand function. So in this case, it's just the domain of F, which once again is A. Right? Any confusion there? So they have the same domain. So then the domain of H composed with G composed with F is equal to the domain of H composed with G composed with F is equal to A. Should have put the A in the middle. My bad. Anyway, so they have the same domain. Now we need to show that they map the same way. So I need to grab something random out of their domain now and show that both functions map it the same way. So now, let little a be anything in A. Then, H composed with G composed with F is equal to what? Using our definition over here of what it is, G composed with F of A is equal to G of F, our right-hand one, of our variable. So it's H of G composed with F of A. You follow that?
Yeah, but aren't you missing your A first?
Oh, thank you. Bracket, this thing of A is equal to, okay, sorry, real squish. All right, now this is equal to h of g of f of a, right? Then that's equal to that, and now let's look at what this one gives us. And h composed with g composed with f of a is equal to h composed with g of f of a, right? Plug that in for the right-hand thing we're composing, which is equal to oops, we don't need that. Which is equal to h of g of f of a. Therefore, the two functions are equal. Therefore, h composed with g composed with f is equal to h composed with g composed with f. Any questions on that proof?
How do you go from there? The second to last thing you did to the last one?
Here to here?
No, there
Here
to
to here?
there.
So, when you have h composed with g of something, that's h of g of that thing. That's h of g of that thing. The same way that we did this. So if I had h composed with g of x, you know that that is h of g of x.
Oh, I see.
Same thing, except for now our x is an f of a. Right? Okay. So let's say you prove two functions are equal. Show that they have the same inputs and that they map each input the same way. Next, we want to talk about an identity function on a set. So once we have some set A, we'll do an example and then we'll write out what exactly its definition is. So if we have A equal to, give me a set, 2, 5, 7, 9. Then the identity function on A, we do ID sub A, is the one and only one function that maps everything in A to itself. So it's the function 2 goes to 2, 5 goes to 5, 7 goes to 7, 9 goes to 9.
Can't we do this in?
Yes. So that's what the identity function is on A. So if I give you set A, then if I say, and its identity function ID A, you instantly know what that is. It's this. Make sense? So now we'll write out its definition exactly. Any questions on this proof before I erase it? Or on any of this? Maybe we'll keep our definition of composition up there for a sec, in case we need to reference it, and we'll come put this other definition right under it. So the definition of an identity function, definition, let A be any set the identity function on A, written IDA, is the function whose domain comma, and for all A in A, the identity of A on A is equal to A. In other words, the way that we can say it is the identity function on A is equal to the set of all ordered pairs A comma A, where A is in A. Take everything in A, map it with itself, that gives you the identity function. Make sense? Okay. One more proof, then we're done for today. So proof, let A and B be sets, let F be a function from A to B. Prove that F composed with the identity on A is equal to the identity on B composed with F is equal to F. Okay, we have to erase this. Proof. Let A, B sets, and let F be a function from A to B. Then F composed with the identity on A is equal to the identity on B composed with F is equal to F. That's what we're going to prove. So these identity functions act like an identity element with function composition, right? Let's get started. So I need to show that all three of these functions are equal. How do I do that? I need to show that they all have the same domain. And then I need to show if you grab any element out of the domain, they all map in the same way, therefore they're all equal. Alright. 1. Observe that the identity, the domain. So let's look at the domain of F composed with the identity on A. Well, that's just equal to the domain of the identity on A. What's the domain of the identity on A? A. The identity on A maps everything from A to itself, which is equal to A. And we have the domain on the identity of B composed with F is equal to the domain of F is equal to A. And we also have that the domain on F is equal to A. So all three of these functions have the same domain, right? Okay. So now, let little a be something in our domain. Then, let's see. What is F composed with the identity on A of little a? Well, that's equal to F of identity on A of A. What is identity on A of A? It's just A.
Yeah.
The identity function maps A to A. Right? So this is just the same thing as F of A. Right? And we also have the identity on B composed with F of A is equal to the identity on B of F of A, which is equal to, what's the identity on B of anything? It's just that thing, F of A. And then we also have F of A is equal to F of A. So they all map it the same way. Right? Therefore, they're all equal. I don't bother plugging in all the words. I think you get the picture there. Any questions on that? So that's going to be a common thing that you're going to have to do from here on out is prove that two functions are equal. What's the strategy for showing that they're equal? Oh, did you have a question?
Yeah, will you go through the second one again?
This one?
Yeah.
So the identity on B composed with f of A is just the identity on B of f of A. But the identity on B of anything is just that thing. Because it's an identity function.
Right.
So it just mapped f of A to what? F of A.
You say anything, but doesn't X have to be in B? It is in this case, but.
Yeah, this has to be defined.
Okay.
That's why we have to make sure that we were grabbing something out of the domain, because all these functions have that as their domain. So they map everything in A to something. So we're guaranteed all along the way that our function's defined. Any other questions? All right, so that's the end of function composition. We'll call it there, and then the rest of class to answer all your questions, do whatever you want. You can take a break first if you need.